Alright, here is the Reasonend Schemer, the Boolean algebra part, and then I guess it will become numbers. Well, we already at numbers. So first, the bits are zeros and ones. Then we define the truth tables for the relationships between the bits. So x oro, for example, 0, then there are two possible values for x and y, where x oro is 0. Here the other way around with the 1, and then funny thing about relational programming, if I pass everything still fresh, I get the complete table of inputs and outputs. So I find interesting concept. And then you narrow it down. You have the complete inputs and outputs, and you narrow them down or something. That seems to be basically the programming paradigm. Then here's ando, and noto. I define them for training in terms of pattern match, which is almost the same. It's basically the same, but way more concise. Funny definition of bit noto. You can also pass it to nando with xx 2 times, and then you get the truth table of bit noto, for example, 0 1 1 0. Another version of bit ando is bit nando y x y s, and then pass the outcome of this to noto. Yeah, not and. Yeah. So then here the half edero is a relation that takes 2 bits and a carry bit, and then this one says whether, well, not carry bit, I don't know, this is the basically the slot for a number that says 1, and this is the slot that says 2, kind of like this. So the equation that it fulfills is x plus y equals r plus 2 times c. And you define this in terms of in terms of an XORO. So that says either of these is 1, but not both. And this says both of them are 1, so this becomes 2, kind of. This says there are 2 inputs. And this is that one of them was 1 and the other one was 0. So yeah, r plus r plus 2 times c. Half adder with 1 1, and 1, there's only the solution that r is 0. And the truth table of this function looks like this. Basically, if either of them is a 1, then the r becomes 1. And if both are 1, then there's basically no remainder. So r stands for remainder. And then c is 1. And it says that there's now a 2 in the equation. Full edero, more complicated, and takes a third argument. Then here is the numbers. So now we are talking about numbers in terms of lists in the symbolic domain. We create numbers in the symbolic domain, which is kind of funny. I feel like that there's basically this tower of abstraction, and now we are recreating the bottom layer in terms of the symbolic high layer. It's kind of a funny twist. But yeah, so here definitions. the 0 is the empty list, 1 is a list with a single 1, and then you read from the front of the list. This is maybe at first this was confusing. At first this was surprising, but kind of makes sense if you read if you define a number in terms of a list. Then probably the first thing should be the least significant bit, so that this here means 6. This is 0, well, 2 to the power of 0 times 0 plus 2 to the power of 1 plus 2 to the power of 3. Oh wait, this means 9, I guess. Oh, 6 is, no, 6 is like this. 2 plus, how does 6 work? 6 is 4 plus 2. Also this is 4. 2 plus 4, like this, okay. Then this is 19, and so forth. So here's the funny thing: if you add a 0 to the front of a list, you multiply it by 2. So yeah, if I have the 1 and then I add a 0 here, now I have this is a 2, and then this is a 4, and then this is a 8, and so forth. Except for the 0. This makes it double. And this makes it double. But the empty list doesn't work, because then it would be 0, and 0 is undefined, basically. This is not a number. Because 0 is represented by the empty list. This is just convention or definition. If I add a 1, then I say times 2 plus 1. So yeah, let's think about a function called Byrd num. Okay, I'm gonna write this in closure, of course. So if 0, then it's the empty list. This is basically the base case. Else it's even. Then we can say. Let me think about this. So let's say that the input is like 2, then the output is supposed to be 0, 1. So basically you add a 0, and then there's something like the recursive call is divided by 2. You return a list where the first element is a 0 and the rest is the recursive call divided by 2. Well, it's this easy, what? Okay. This turns out to be correct. Byrd num, and then divide n by 2. Now, yeah, will be fine, I think. Divide with this 2, then this will, for example, say 1. So yeah, this would go into the next branch. Odd. Then you add a 1 and you do the same thing. Okay, cons 1. Yeah, like this, right? Oh, you also need to say -1 true because you added a 1, so basically you are done with one more kind of, yeah. Okay. Build now. It's kind of funny. This is already what you need. This returns like this, and then yeah, this should be 0, 0, 1, right? Yeah, and then this has another bit at the front. Yeah, okay. And what is the 0 should be the empty list. Yeah, sure. And then 1 should be the list with one bit. Okay. And 2. Yeah. Okay. Okay. Redefine build number 0 is the question at the last cont line. Yes. Is there anything interesting about the previous definition of build num? Only one cont question is true. There's only one cont question true. Is even odd or 0? Yeah, it's true. So the ordering doesn't matter. Can we rearrange the lines? Yes, this is called the non-overlapping property. Thank you to Dijkstra. Oh, okay. I guess this is when you have a disjunction where nothing is overlapping or something. Which, yeah. It appears rather frequently throughout this and the next chapter. Okay. Non-overlapping. I guess this is important. Okay, this is non-overlapping. Because otherwise in a cont, if there are multiple branches would be true, then it just picks the first one. So that, yeah, there's a difference there. With non-overlapping, you can rearrange in any way. What is the sum of this and this? So the sum of this should be this. Yeah, this is 1 plus 1 is 2. What is the sum of... Okay, so this is... well, yeah, nothing, 1. So this is... one sec. This is the slot for 1, 2, 4, 8. So this is the number 8. And then... I could write it like this. So 8 plus 1, 1, 1. Yeah, that will output kind of... This is kind of like the XOR of... You can take the XOR of each of these bits, and you would get to this. Yeah, and this would be 1 plus 2 plus 4 plus 8. So 17? No, 15. Yeah, so you could basically flip around the zeros and ones here, and it would be 15. What is the sum of 1, 1, 0, 1, and then the other one is 0. That should just be the same. This should output exactly this number again. That happens to be 19. Okay. What is the sum of this and this? also 19. So if either of them is nothing, the output would be the same thing. What is the sum of 1, 1, 1, 0, 1? This is... man, I want to write a function that... it takes a list and returns a number. Let me quickly... so that... or map... x, the math power 2 to the power of n times 2 to the power of idx times n. I think this is correct. Apply plus num 0. Ah, wait, this should also output 0. I think it outputs 0, yeah. Then, so, wait, well, this would be 0, this is not allowed though. I'm just gonna do this. This is actually an error, I don't know. Okay, this is not a number. This should be 1. Okay, works. And then I can also cast this to a long, I guess. We don't have rational numbers. I could say long here, I think. Yeah, good. Okay, this is correct. 23. Yeah. 24. Wait. 1, 1, 1, 0, 1, and 1. Yeah, that's true. This is 23, and then so this plus this. It should become. So yeah, this is basically carrying. Yeah, this is because both are 1 here. It makes a 0, and then it kind of goes like when you do addition. On paper, there was that it carries, and then I have a 1, 1 here, and then it carries again, and then a 1, 1 here, and it carries again, I think. And then here it says that one of them is true and the other not. So there should be some XOR here. And this carry thing you can figure out with an AND. Yeah, and then here 1, I think. Is this the outcome? No. Yeah. Okay. Yeah. And this would be. I don't think through it anymore. I just wrote the code for that. Yeah, it's 24. Okay. What is the sum of this and this? This is 24. Which number is represented by? So you take a number and then you add 1 at the end. 1 at the end. It means that you take you double. Wait, 1 sec. Let me think through it with the 1. So if I add a 1 there at the end, so 1 looks like this. Then if I add a 1 at the end, I basically say that first of all, it's the same number plus something. Yeah, it depends on what x is, yeah. It depends on the count of x, kind of like. I can take the count of x and say that I would end up sort of with this, like, it's plus 2 to the power of the count of x or something like that, roughly. I'm just enjoying this code right now. Yeah, I guess it's just true. It just works. Yeah. Yeah, it depends on what x is. Okay. Which number would be represented by what? Which number is represented by a list where the first thing is x and the rest is 1? It depends on what x is. Which number would be represented by what? This is the same. So if this were 0, okay. So if this were 0, I could write it down like this. Yeah, and this is 2. Yeah, this is 2. Which number would be represented by, if this were 1? Yeah, then I could write it down like this, and it would be 3. So which numbers are represented by any x and then 1? Two and 3? So if x is only ever 0 or 1, yeah. This is only ever 2 and 3. Funny, yeah. Because I say here this is a 1. So this is saying that this is, yeah, well, it's saying that it's either of those two lists, which mean 2 or 3, yeah. And the same goes for a number like this. Yes, I say for sure that it will be 4 plus, and then it's either plus 2 plus 1, or it's 4 plus 0 plus 0. Am I correct? So 4 and 7, what? So x 2 times the same number. Yeah, true. So either x is true or false, 1 or 0, yeah. So it's either this or this. Okay, there's no other solution. So this is 7 and 4. Yeah, okay, so either of these two. Yeah, true. Okay, I'm following. Which numbers are represented by a list with x, then 0, y, 1? Okay. I'm just gonna write down all the cases. So if x is 0, I guess I can write it like this actually. Let x be 0, then 0, 0. So and y is 0, 0, 1. So this is the first case, and then I have this case. Then this is like this. Okay, and then I have. Yeah, it's the Cartesian product of these two possible values. 0, 0, 1. Then substitute this in here. I do it so that I get, like, I don't know, training thinking about this, because sometimes you think about some kind of basics and then suddenly you have like brain circuits that basically apply something, and then suddenly it's like useful to have these brain circuits for some problem, because something more complicated is suddenly easy. I think like this. 8. Okay, I'm doing something wrong. X is 1. One sec. That looks wrong. There should be a 1 here. And Y is 0. That was just not correct. 1, 1. I think that looks like that. And then X is 0, Y is like this. Okay, there's a 9 now, yeah. So 8, 9, 12, 13. Okay, I've flipped them. Okay, and now, wait, I can't. Can I just say run X, Y? Oh wait, run X, Y, R. Let me try. Let me try to use the logic engine to write this. So then I say bit2 to basically constrain an X to either 0 or 1. So just like that. So if you say bit2 X, it's either 0 or 1. So I can say bit2 X, Y are 0 and 1. Then I have this list. So I'm gonna use the logic list. Okay, this is gonna take the logic variable X, and then I say 0 and Y and 1, and it's a proper list like this. And now I think I can say project, because I'm using something that's not a relation now. This is this num. And now what actually will this do? Also yeah, now I can say R is the outcome of this num. Okay, this some error. Project vars and goes. One sec. How does this work? Extract the values bound to the specified logic vars, non-relational. Why was I thinking that this would? I just say that R is bound to this list. Then extract the values. How do I? Okay, I have another way right now until I get more training, but I could just say R is this, and yeah, then maybe I make these local. So now I just get all the lists, all the possible lists, and this is actually useful. This is basically this Cartesian product that I was writing down up here. So now I can just use closure, and I say, oops. Okay. I just use closure. Or maybe I say map juxt identity num. No, like this. So I've used the logic engine to list out the possible lists. At least that. instead of writing it down myself. Okay. Okay, so here we are with this 8, 9, 12, 8. Yeah, it's different order, but yeah, 8, 8, 9, 12, and 13. Which numbers are represented by a list? X, U, Y, C. Okay, that's... Now there are more possibilities. So it's the same 8, 12, 9, 13. And they show up, yeah. And then additional, they all the versions where this is 0 show up. There would be... once again. Wait, what? So this is constrained to not ever have a 0 at the end. I see. So actually this... oh, this is even wrong. I see still fresh. So, but actually C is kind of constrained to be... yeah, I can write this down here as well. Let me quickly say that the last element of this list is never 0. Let me quickly write it in terms of logic relation. Last is not 0. It's a little bit silly, but yeah. List. So either you are an empty list, then it succeeds, or you are not an empty list and you have an element at the front and you have some rest, then it's the recursive call. Or you have, or you are a list with a single element that says 0. That says 1 sec. Or you are a single element, I can write it like this, and that is not equal to 0. Maybe this is simple, yeah. This is one possible way of expressing this notion that the last element is constrained to not be 0, yeah. So in that case, C would be constrained to be 1. Let's see if I did this correct. I did this not. I did this. Wait, the last is 0 here as well. I did not do this correct. Is this call here correct? Oh, I'm not I'm not using the function. Last not 0. No, wait, this is still not correct. Oh wait, it's all the possible things. 1, 2, 3, 4 elements. This one shows up, so this is already wrong. Okay, let me figure it out. I'm pretty sure this makes sense. I'm finding all possible branches, and then it says that it can also be a 1, and okay, not entirely sure, but I just throw out the empty list. I think this would in this case work. Okay, but this was a little bit lame now, though. Yeah, this is if I know core logic better, I will understand how to, because this is basically possible. So it's possible that the list is just, the list kind of goes on, and then D is the empty list, and then this is allowed, and this would just work. Last is not 0, but what about the empty list? Well, I kind of say that the list has at least one element. So yeah, I guess this also kind of has some kind of merit. Yeah, you could. Yeah, I guess you could say this. Either the last is not 0 and it has a single element, or it's empty. And the list. So now, in principle, the empty list would be allowed for this. Here I should say that D is not empty. Yeah. This would work. But yeah, I'm not entirely sure yet if this is how you do it. It seems contrived somehow. There's way too much code now. That's not the case in Clojure. Clojure is good. Okay, now like this. No, I'm not correct. Did I? I'm not correct. Okay. Oh, I say cont e. One sec. Cont e fail doesn't make sense. Hey, I need to say and. Wait, I need to say and. This is another thing. Also, then you don't need the cont e. Okay. Okay, now it has 0 output. This is empty. So this is not empty. Oops. I wanted to say it's not empty. I want to say if it's empty, it should fail, and then it should not try any other branches anymore. So condi is not the correct. Condi is not the correct structure, because this is an OR. I need it to fail here. So yeah, I think there's cond R, soft cut. Once the head of a clause has succeeded, all other clauses will be ignored. Not relational. This is for sure not what I need. Cond U, once the head first goal of a clause has succeeded, the remaining goals of the clause will only run once. Okay, it's also not what I need. Okay, one day I will figure it out. One day this will be so obvious, I think. basically say non-MTU, or yeah. Let me try this. Yeah, it says that it's at least a pair or something. I think this will work now. Yeah, okay. Yeah, not sure yet. I think here you can say pair or cons question mark? No. Okay. Yeah, don't take this too seriously. This is me trying out. But yeah, now here I have actually programmed some core.logic now. I mean, at least this problem I'm solving. Given any kind of list, give me all the possible number representations and numbers. Okay, which are these numbers? This is the same numbers. Which number is represented by just a list with x? Okay, I can make the same game. It's a bit. Yeah, but there's only one number. So yeah, that's true. Yeah, there's only one. Yeah, only one is possible. That's true. The only possible one is this, and this is 1. So if you have a single bit in a list, it always is 1, because 0 is thrown out. Which number is represented by this? Wait, always 2? So 0, 0 is also doesn't make sense. Yeah, because the last element is 1. So that, yeah, if I do the same game here again, I have x, and now I put a 0 here. I only get 2 out. Yeah, that's true. That's true. Which numbers are represented by 1 and then c? And this as well is only, okay, I'm not gonna write it down long. 1, c is only ever 1, 1, because 0 is not at the end of a number. And that is, no, whatever. What is that? 4 or something? No, 3 here. And depends on what c is. What? Okay. Which number is represented where c is the empty list? Okay, in that case, I have 1, and then that's 1, of course. Which number is represented by 1 and then c, where c is also 1. So it's append 1 to 1, and then it's 3. Which number is represented by a 1 and then a c, where c is the list 0, 1. So then I call append basically 1, 0, 1, 6 or something, 5. Yeah. So which numbers are represented by 1 and then this? All the odd numbers. Cool. True. I guess makes sense. These are all the odd numbers. You take a 1 and then anything. And then all even numbers. Yeah, it's all the lists that start with 0. These are all the even numbers. All even numbers not quite, because there's also something with the 0 or something like that. Which even number is not of the form 0? So there's also a 0. except 0. For which values of C does 0 C represent a number? So there is also, if C is the empty list, then it's not actually a number, because this is not a number. For all, a number for all greater than 0. Yeah, if C is a number, yeah, it needs to be greater than 0, as you can't put it at the tail of a 0. You can put it at the tail of a 1 and that will work, because that would output the 1. Okay, which numbers are represented by 0, 0, 0, 0, and then the rest C? So everything divided by 4 or something like that, I think. So starting with 4. Oh, yeah. Every other even number. So every other even number. Oh yeah, it skips one. Ah yeah, true. It skips every even number. So it's all odd numbers, and now it skips everything divided by 2. It skips everything divided by 2, I think. The other way around. It's only everything that is divisible by 4. Sorry, yeah. Every even number that is divisible by 4. Interesting, I guess. Do I make sense? I'm gonna. So let's say take 10 of these numbers, right? So a list. So wait, C is a list. C is a. Let me define. This is numo. So this is a list of zeros and ones. Or the empty list is also allowed. Yeah. So wait, the empty list is allowed. Okay. Then what is also allowed is that you are a list of 1. Yeah. Then what is not allowed? This is not allowed, kind of. I guess I can say here fail. Okay, and then what is also allowed is that you start with A and the rest is D, and then A is a bit2 A, and then the rest is numo. And then, but wait. Also this is non-empty. Yeah, D is not empty, yeah. I guess this, I'm not entirely sure if I do it absolutely correct, but this is probably like 1 too complicated or something, and if I understand more, then it would be like 1 more simpler. But yeah, this would be a relation where this thing is a list, I think. Where this thing is a number. Okay, so if I say run to, and then C is a numo. What do I get now? The empty. This is the 0 and the 1. That's already correct. Oh shit. No. This never ended. Numo. So these ones worked because there was a 0 and 1 was still kind of, and then there's only this recursive call. I say here non-empty D. here I say that this works, but now you get I say numo list. That was the problem. Yeah, but I think that now I probably also get the or does this work? Okay, yeah, I also get the list where there's a 0 at the end, so this is not allowed. So I'm gonna try this again. Yeah, this must be correct, I think. Yeah, at least it's correct. It's probably contrived, but it's at least it's correct. Okay, so give me 10 numbers. Just give me 10 numbers. Okay, and then I say what's response? So if this makes sense. What did we talk about? Okay, so there's a structure of this. It's 0, 0, and then plus a number. Yeah, like this. Append a number. Yeah, that is R. Okay, so R is all the lists. R. And now give me all the. Yeah, I'm gonna put this here in a local. Yeah, so these are 10 of these, kind of, like 10 possible of these R's. Oops. Okay, so wait, this is a list, yeah. So map num, or map Chuck's identity. Okay, this is the outcome. 0, 4, 8, 12, 16. Oh, so yeah. I'm not sure in which order I output this now. This is everything where you skip the even number. So this was 4, 6, then 8, yeah, then 10 was skipped, and 12, yeah, true. Then 14 was skipped, and then 16. I think that's correct, yeah. But this is also everything divisible by 4, I think. Okay, kind of cool, yeah, cool, okay, alright, okay, alright. Starting with 4, which numbers are represented by this? This is all the even numbers, where the 4, where the 2, wait, 1 sec. All even numbers, and now I say 1 plus 2, and 2 is always part of the number, so for sure it starts with 2. Wait, 0, 0. Wait, this one is wrong. Ah, yeah, this one is not allowed. Oh, this should also be a numo. Maybe like this I would. Oh no, this would. Ah, this takes really long. What the fuck? Does the ordering here matter? Ah, yeah. Okay, interesting. Okay, this would narrow it down. This is so interesting. The ordering matters like crazy. if I first say this is numo, so because I get like shit tons of this is recursive, and R is still not thingy. R is still a list where everything is still possible or something. So it's like a lot of possibilities. Yeah, this is like 1.2 seconds, and then if I first say R is this list, yeah, it is something that is instant, 4 milliseconds. Very interesting. Okay, so let me say that R is also a number. 2, 6, 10, 14, 18, 2. So it's somehow, it's again all the even numbers, because the 1 is basically masked away, kind of, if you want to say it like this. The first bit is cut out of the number. So the 3 doesn't exist, and then the 4 would have been this. The 4 would have been. The 4 would have been this. But the 4 is also cut away, because I say that it's not divisible by 4. Everything that is not divisible by 4, I guess. No, wait, that's not how it works. Right? By saying that, by constraining this to be 1, I say that it's whatever number plus 2. Just give me all give me all even numbers and then plus 2. So it's kind of like k element, the natural numbers or something. How do you say that? K, n element, n, then k, something like 2 times k is n or something like that. So all, whatever, I leave it, leave it for the moment. Okay, what do they say? Every other even number starting with 2. Every other even number starting with 2. I guess it makes sense. Okay, I'm making a cut here. Okay, so now I've installed Rocket. I quickly want to check. So Kader, this is the thing. Just out of fun. And Kadade. Ah, yeah, true. Kadade needs a tree. Like this? No. One sec. This is the car of the. Oh, Jesus. Let me do it. Okay, Kuda, this is this. Now I say Kadere. That should be the 2. This is only the. So yeah, this is the tree 2. Yeah, now you could, for example, say Kadere, and it's 2. But let's say kader, and then the kadera, kader, I think, and kader would be the rest of this thing. So it would be no, undefined. This is undefined. Okay. Or maybe it's called kader. Oh yeah, it's actually. Oh, I said this wrong. Okay, it's called kader. Okay, kader. And then you say, let's say this is 3, then this is the list 3. Yeah. But yeah, if this is 10, say, say 30, or something like that. Now it should be 30, 40. Yeah. So if I say ka de adere, I think ka de adere is 30. So I walk the
this is a language that talks about binary trees. Is this true? Binary trees. It talks about. Are these binary trees? Yeah, there's always the first and the rest, right? This is two branches. Yeah. Okay. Yeah. So it's actually a language that in syllables talks about the branches of a binary tree. So I don't know. There's actually something like there's a concept there. Just a curiosity maybe, but I find it funny that there would in principle be a language where this is a construct of the language. Yeah, and the people that speak it would actually just understand what you mean. This is also a thing. So there's kudder, and then 1, 2, 3, 4, 5, 6. Now I say and it's just the rest of the rest. And then I say one sec. I need to train it. This is like supercalifragilisticexpialidocious or something. Once you know how to speak it, it becomes a thing. Okay, so this is kudder, and then and then one sec. And and then it goes up. Once you're able to speak it, but the funny thing is, it would be a word in your language. Like you wouldn't even need to think about it. Like you would also understand it because it just would hook into your language understanding. Like I find this kind of funny because I understand car and kudder. I understand perfectly well. I even understand kudder. And I also understand kudder. I can literally say that it's a 3. Oh wait, it is a kudder. Oh yeah, true. It's a yeah. The 3 would be kudder. True. But yeah, there would be, I don't know, it's like it's not from the table that people would actually understand this in terms of the way that you also understand language. I find this kind of funny because it's like yeah, it would be a word for the first element of the second branch of the binary tree. It's just a funny thing. Okay, that was the excursion into. Okay, so this is why they say down here A, D, D. This is for kadera and kadera. Yeah, okay. First, second, and rest of the rest. This is the enclosure. A bit too much. I need to start this again. Maybe evaluate anything. Okay, was some error somewhere over there. In closure, the kudder, we say drop 2. Drop 2, right? And this is 3, 4, and in scheme, the kudder is 3, 4, right? 3, 4. Yeah, it's the same. We say drop 2 instead of kudder. No. Slightly different approach. That is, yeah, seems to be more modern. Okay, what is the value of run star? Then anything? Oh yeah. Then say greater 1 no, and then the list with the element 1. This is just true. It's so it's greater than 1. Oh, oops. Yeah, greater than 1 means yeah, it's at least 2. Yeah. That was what we found out. So this will not succeed. It will not succeed. So the queue is never bound to anything. So the outcome is empty list. In case you missed the intro to miniKanren. What is the value with R? Okay, run star R greater equal R. So yeah, these are all the numbers. So yeah, it's this structure. Yeah, this is kind of the. Yeah, it's interesting. Yeah, it's not a list of numbers. It is a list that says that there's at least 2 elements. Roughly, something like that. Does this mean that always succeeds when R is fresh? Yes. When R is fresh, it always succeeds. It narrows it down to this structure, and that's it. What is the value of run 3 x y r, and then add a row? Let me go. Make sure that I have add a row. I don't have add a row. We have not seen add a row. We understand, however, that add a row b n m r satisfies the equation. B plus n plus yeah, b plus n. Okay, these are two numbers. So plus m. Okay, three numbers equal r. So where b is a bit, n and m, and r are numbers. All right. Okay. So if I say run 3, add 0, okay, then that's something to think about. Okay, 0 says don't increment by 1, kind of, because b is a bit, I guess. And then x and y, okay. And then r, okay. I mean, this is in general this is x plus y, r is x plus y, I guess. Oh. What is this? Oh, so yeah, true. We find adder's definition in frame 104. What is the value of this? Do you need to scroll down? Adder is quite complicated. Oh, this is a more generalized version, yes. Depends on full adder. Full adder was that you take 2 bits, you take 3 bits, and then you return this function 2 plus 1 plus 2 times c, well, r plus 2 times c. Okay, I'm gonna type it in basically. Yeah, coming up with it myself right now would be quite a challenge. Okay, I'm gonna type okay, b n m r condi. Okay, so if b is 0 and m is empty, I was quickly considering to use this MTO instead, but it's equivalent. Yeah, it's equivalent, so I take the version that they have as well. Okay, so when b is 0 and m is nothing, yeah, that's true. Then r is n, because then these two things were both zeros, so then in that case r is n. Yeah, okay. R is n, n is r. Okay, this is the first case. Okay, the same way you can do exactly the other way around. Yes. Okay, now comes. Oh, there's one other thing you can also say about m in that case. N is 0. You can also say that m is positive. I don't understand why. Is r always positive? Why this positive here, not here? Why is this different? Okay, I'm not sure about this part right now. Okay, next case is when b is a 1 and m is nothing. B is 1 and m is nothing. Then you can take the n as a number and you call it recursively adero. Let me think through this. Basically, you remove the b kind of, and you say adero with 0, so that one of these cases becomes true, and n is not touched, n is goes here. So basically, we wait until the first thing here becomes 1. Yeah, a 0. I guess down here we say minus or something. No, you don't need to. No, never mind. You only work with the numbers. Okay, so yeah, but in this case, m was the empty list, so I can collapse it in this way. I need to say here list r. Okay, then the same way, like this, and then m here. Yeah, or flip it. Don't think this would have mattered, probably, but to be consistent. Okay, now another case where they are both 1. N and M are both 1. In that case, oh yeah, okay, you say that R is at least all the numbers that are more than 2 or something like that. This is what this says. These are all numbers that are bigger than 2. And you say that A and C is the outcome. So full adder here, full adder. Oh, this is, yeah. Okay, this is quite intense. And I say A, C, R. I say that R is a list. So yeah, because M and N and M are both 1. Then that way I kind of know that the outcome is at least 2 and maybe 3. And this is what this is saying. This is what we said earlier as well. That this means at least 2, and then the all the numbers starting with 2. Oh, list AC nil. No, this already says I'm 2 or I'm 3. Yeah. If I would, I also need to say that R is a number. Basically, I'm not constraining these things to be zeros and ones, I think, anywhere. So A and C are still anything. I guess they are constrained. If I pass them here to full adder row, then they will be constrained. Okay, full adder row. So this is the bit that we're still talking about, kind of. And then add 1, 1, yeah. Ah, yeah, A and C. Okay, now I sort of see the structure. This means that there was a 2 in the mix. That there will always be a 2. Yeah, and the question is only if this A is or is not a 1. That's like still possible. Depends on the B. So if you pass in a B here, then if this bit is on, then C will be on and A will be 0. And otherwise A will be 1 and C will be 0. A will be 1 and C will be... No. C is never 0. C is on for sure and A is maybe on. I think I could also say 1 here. Pretty sure, but it doesn't matter because the full adder row is taking care of it. Yeah, okay. So here it bottoms out to become a sort of a bit operation. A and C, that means that B is bound. Basically the outcome of this thing, so that R is now a list with 2 elements, yeah. That said either 2 or 3. This kind of makes sense. If N and M are both 1, then the outcome is either 2 or 3, depending on the bit here. So yeah, this branch makes sense and outputs a number. A number of 2 elements that represent 2 or 3. Okay, so far I'm following. Oh, Gen adder, holy shit. Yeah, this is quite intense. If N is 1, you also say Gen adder. Okay, and Gen adder. Okay, man, this is crazy. At least for my level of logic programming, I'm not sure who would come up with this. List A X is N. Dy is M. Okay, these say that there's at least 1. For N and M, there are at least 1. Then you say that Y is possor. That means that Y is also Y is not the empty list. At least 1 as well. Then C is R. So R is also at least positive. And then because C is also positive, R is I think at least 2. Full edero B A D Z E. So B is still this bit that we passed in. So we basically we destructured the first bit of each of the numbers of n and m and r as well, because it's relational. So we say that there are 3 numbers, and for x you don't need to say posto. And this one is allowed to be. So this one was this one was only the one when we passed it in here. The other ones are not one. I guess the idea is that it would fall into this case. So yeah, here we kind of know that. We say we constrain it here. Gen adder basically constrains by saying this part. M, yeah, by saying this line, it constrains M here to be more than 1, because it has at least 2 elements. Okay, so full adder B80 CE, and now we basically took the first bits. Then we say full adder. This is always how we bottom out to circuit level things, basically. XOR and NAND. Or AND, I forget NAND. Either way. So this B always is basically dealt with after the full adder, kind of. So B and then A and D, these are the first 2 bits from the input numbers, N and M, and C is the first bit of R. So yeah, that is the number 1, kind of, for R. So whether R is even or odd. And E is the E means that both of these bits were set. That's what E means. So it's 1. If there were 2 inputs, then E is 1. And then addero, the recursive call. E is now a single bit. So E is a single bit. 1 or 0. So for B. And then X, Y, C are the rests of the numbers. Okay, damn. Okay, full addero and then addero. Okay, you kind of see how this is the recursive thing where these are numbers, so list, and this is a single bit. Yeah, and basically it's tied into the output with this R. It's kind of saying what kind of number is the rest of R. And we sort of took the first 2 bits from the numbers that we were adding and said that either they together make a 2 or a 2 or a 3. That's what you can do with full addero. Yeah, and this is basically the thing that you carry forward, this E. This is like when you write down, when you add like this, and you would see these 2 ones here, and you would make this little carry. And you would write this here, you would write it here. So this would be 0, and in this case the E, this carry bit, would be 1. So this is basically the E. And this is N and M. Then I only look at the first elements and do this operation and assign E. And yeah, the rest I carry forward the computation. And I also assign the first element of R, the output. So this is the first of the output. So R basically shows up here at the bottom. So 0, blah, blah. So this is R, and here I just talked about the first element of R. And here it's the recursive. Yeah, this is happening here. I kind of see it clearly now. I could give it more names. I mean, this is the C. This here is the C register, kind of. Yeah, and this one is A, and this one is D for some reason. So yeah, you sort of build, so to say, this R. But of course, the beautiful thing is it goes in both ways. So you might as well say that you build the inputs. Chen adder B and R, then there's an error here. This says when n is 1, then Chen adder. Then when m is 1, and n is bigger than 1, and R is also bigger than 1. In that case, adder B 1 and R. Okay. Then m was 1. How does this even make it smaller? It's smaller. So then we go here and we say Chen adder. Okay. So we build up a larger R kind of. Okay, and else if n is bigger than 1, then Chen adder. This is probably the other way around or something. Chen adder. Oh, Poso. Oops. I have Poso. Numo. Here, constraint to Numo. Yeah. I don't think this will break anything. Bit too. Numo. Non-MTO. Oh, yeah. Do I have everything now? Also, Edero. Yeah, okay, klar. Okay, Chen Edero. This is the last B and R. Do we flip the inputs? No. What? So Chen added. Yeah, okay. If it's 1, then this. This is interesting. Why? You feel like that there's like one Chen adder call more than you would. This is if n is 1, then Chen adder like this, and if n is bigger than 1, then Chen adder. This probably has like a reason, but at first glance it looks a little bit like, wait, couldn't you just only write this once? Sort of like else? No, yeah, either way. This was crazy. Okay, but yeah, this adds 2 numbers. It doesn't even fit on the screen. Well, it fits both. Yeah, it fits. On these base cases, I understand. Here we constrain m down to Poso. R is for sure a number, is at least 1. Then B is a 1 and M is nothing. That means somehow that you can throw away the M. You collapse the B, you make the B a 0 and then add the row with 0, so we find one of these base cases because one of the lists was nothing. This is important because here we need to bottom out this case. And this is basically this situation. One of these lists was empty now. Yeah, and then the carry bit was empty because E was 0 in this situation, and then the outcome is then I would be here. The outcome is n, but n was also empty, so that's fine. But this way around is not fine somehow, because m needs to be at least 1 in this case. So it actually matters quite a bit. N and m, these matter quite a bit. What you put there. 1, if one of them runs out. Not sure if I fully understand it. So here is the case where one of them runs out first, but we still carry bits. In that case, you add 0 to 1 in this thing. If they are both a 1, yeah, then you know the case that it's either a 2 or 3. Actually, we walk into this case here, in this case. So I guess this makes some case simpler, so that I don't run into this problem. So you never run into the problem where both lists are empty or something, I think. So if I say run, and then entero 1, and then yeah, like the antilus and the antilus, it should be 1, right? But it's illegal. Something is illegal. Oh, poso is still not defined. Oh yeah, it is 1. Okay, this is 1. Good. It's correct. In what case does this understand? One sec. So it went here. No, it went here. It went here. And said run it recursively and then substitute m for 1. So that in the second recursive call this one was true, so r became 1. So that's what I see here. Okay. Yeah. Okay. If one of them is 1. Oh yeah. Yeah. This is the 1. I call num on it. It's 2. And then something like this. I think this should be 4 now. 6. Whatever. That's probably true. This should be 5. Wait. This is 4. So yeah. This is the number 3 plus 1 is 4. Yeah. And then the number 3 plus the number. Is this 5? I think so. Yeah. I'm quickly checking. Yeah, this is 5. Okay, so this is 1 plus 3 plus 5. 9. 1 plus... Yeah, 1 plus 3 plus 5 is 9. Yeah. Okay, this works. Okay. Yeah, it's a logic engine. It's a logic relational arithmetic. This is crazy. Wait one sec. This is... yeah, this is really cool. Okay, so let's say add... Do I need this one? Yeah, okay. Let's say add... Byrd num... Let me think. This outputs a list, but I need to... so yeah, I need to... one sec. One sec. Doesn't make sense. Oh, wait. Take the first element. So yeah, I would need to... no, this... Does this work? 1, 2, 3... Yeah, it works except for the... So, like this, then it would work. Say, build num 5... Cons... One sec, what is this? This is because of our closure. Yeah, closure basically doesn't have proper lists. It doesn't have the concept of proper lists. It just has collections. Yeah. So wait, I just return logic cons here. Yeah. That also solves it. L cons, logic cons. Yeah. So I think now build num. Yeah, I think this is correct now. Okay. Yeah, this is a logic list now. Yeah. Okay. Cool. Okay. Build num. Say 2 and 3. Okay, this is 5, right? Yeah. Put it into symbolic domain or my domain. Closure domain. Oh, error. Error now. Oops. So I accidentally. 6. I guess that's true. Yeah. Okay. Okay. And now the cool thing is that I say, yeah, give me all numbers that make a 6, or give me all numbers where x and y together with 1 make a 6. Is this multiple numbers? It's no number at all. Wait, how is this nothing? I need to also say that these are numbers. I guess. Really? No, then it never ends. Okay, I don't understand it yet. Let me... yep. Why do I say 6 here? I need to say build number. 6. Okay, no? Yeah, okay. There is an outcome where they are... the x is nothing and the y is 5. Yeah, nice. Damn. Oh, this is so cool. Holy shit. first and then oops. So 0 and 5 is a possible solution for 1 plus something is 6. So if I get all possible solutions, there's only 0 and 5. Why not 5 and 0? What the fuck? Ach, first. Map. Oh, this never ends. Okay. Okay. This never ends. Okay, what if I ask for 10 outcomes? Oh! What the hell? I didn't. Achso, okay. Achso, this also never ends. Okay. So it immediately starts never ending the moment I ask for more than something. 2 is okay, and 3 now it looks and never finds. 3 is also good. Okay. Interesting. So it finds all possible ones. I guess before I would find. Let's see. Yeah. Okay, these are probably all possible ones. Yeah, I guess I can try. I can actually literally try. What if I say 5? I'm pretty sure I get. There's still another possible one, I guess. 4 and 1. Okay. But 10 was not good. 6 is still okay, and 7. Now there's nothing there. Nothing anymore. Okay. So 6 was still good. Okay. So this is something I would have to learn. How to say. How to not have something that succeeds, and there's a lazy branching of possibilities still going on. Build num is sort of. This doesn't get bigger anymore. This is just this number. So x and y are still allowed to be any number. Yeah. So yeah, okay. So actually, what I could do is I could say that, like basically, but this is now, I don't know, this is some trick, but I could say that x and y are for sure less than 6, right? If I add two numbers, this is another invariant. Yeah. So I guess this way you could narrow it down. This would maybe be something that you add here to add a row. Something like smaller than, right? Smaller equal nr and smaller equal mr. I'm pretty sure this would be kind of valid, and then it would narrow it down, and then I could ask for all possible ones here without an infinite thing. Okay, very interesting. Also interesting that you run into these infinite lists. That was when I tried to use core.logic. I sometimes ran into the cases without understanding enough how everything worked. Yeah, I then was basically lost. So that's why I decided I go through this book so that I understand more of miniKanren, so that I understand how to actually use it. So yeah, here I see the edge of something that I would need to understand. If I put a star, I die. If I put a 6, I'm fine, because these lists are still infinite. So you probably want to narrow this down somehow, or something like that. Or you say that, yeah, I only care about the first or something. Then of course you don't have this. You have a different problem then. Yeah, very interesting. Okay, it's this one all. Alright, and here is the last part of the bit chapter here. I have understood something. This chapter is called A Bit Too Much, and this is a play on the carry bit, because if you add 2 bits, then there's a bit too much, and you need to carry it. So this is this bit too much, I think. At least it kind of, yeah, fits. I think it's a play on word on this. Play on words. Okay, so I was looking through the structure of this outcome of edero, and here we are going through gen edero, how gen edero produces values. So I kind of walked through this once, so I have, yeah, quite some idea of this. But yeah, coming up with this yourself is advanced. not something I would be able to do at the moment, I think, but yeah. Gen adder, given the carry bit b and the numbers n, m, r, gen adder satisfies b plus n plus m is r. Okay, here I am. What about the other use of gen adder from addero? The other use, yeah, then in this case n was greater than 1 anyway. So it didn't matter. It didn't matter that we didn't constrain n here anymore. It was already constrained to be more than 1, so. Then it would fail for n being 1. It would fail. Yes, this greater equal is the same as pos x here. But if we would put pos x here, then we would fail in this other situation. So we need to keep this open in this case. The way that we have set up this function. Okay, so gen addero. That says that b is a bit, n is a number, m is a number, and r is the outcome. So b plus n plus m is equal to r. This is what it's doing, yes. And how is this different from addero? It's actually not different, it's the same. But gen addero is implemented in terms of addero, and addero is implemented in terms of gen addero. It's a little bit like a meta-recursive adder, I guess. It says you can bottom out. It's only this function that bottoms out at things, and this one adds the bits. So this one adds the bits, and this one bottoms out the cases, kind of. That's the structure of the algorithm. And there's here one. So I guess it's mixed. This one also bottoms out some bits. This is actually sort of the bottom call of full addero. Otherwise, one of them is 0, so one of them becomes the outcome. But otherwise it goes here, and it says that it depends on the bit, on the carry bit. But yeah, it always says that there's still work to do, so I'm gonna call gen addero, and gen addero says that I'm gonna decompose the lists, and I'm gonna look at the first bits, and then I'm gonna use my circuit full addero to reduce the problem down, including the carry bit. That's kind of the important piece that basically also if you write down this manually as a human, you notice that adding is very, very easy because it's an XOR. It's an XOR, it's an XOR. But the hard part is the carry bit, I guess. A little bit, and I feel like that the structure of the carry bit is. This is the reason why we have sort of this complete thing in the first place, and that's also why the chapter is called A Bit Too Much. Because there's one bit that is basically driving the complexity of this adding notion, and you can not reduce the complexity. It's inherent in the problem. It's one bit more if you have 2 bits it means that now you need to worry about the one that comes from the past. Oh yeah. That's my interpretation. Okay, I'm almost through here. Plus, yeah, no, we also implement plus. Okay. Provided that n is positive and m and r are greater than 1. What is the value of give me everything that is an x and a y, and the x and y satisfy that there's an adder row 0xy, and then there's the number, so I can call it a Byrd num 5, yeah. Yeah, I already played around with these things. This would be everything. This is like 1 plus 4 and 2 plus 3 and 3 plus 2. Oh wait, this never ends for me, I think. Ah, did I do something wrong? Ah, no. Okay. And that works. Okay, that works. Why does this work? Earlier I had something that was infinite. Yeah, okay. What was the other thing I did earlier? Here. Oh, I don't need to constrain him to numo. This is actually a mistake. I see. Okay, because here I say there are infinite lists. And that's actually creating a situation where they never end. Ah, okay, so I could have commented this out and get the 6 outcomes like this. Yeah. Okay. Whoa, this is so good to know. Holy shit. Okay. Yeah, this is really important for me. No. Okay, so here I actually never say that something is an infinite list. I constrain these down to be positive here. And positive, but positive does do this a little bit. It says A and D, that there is a rest, and then there is a first. There is a first, and there is a rest. Also, I say numo here. But because n doesn't have this, yeah, n is never constrained in this way, and that is the important thing. Oh, that's so good to know. Yeah, I'm gonna meditate on this. How does this work here? N. I wonder in what ways n basically grows, because n does grow. So n only ever grows because we set it equal to r in this case. In this case, we set it equal to r, and then it's grown. And that's so interesting. Okay. Yeah, and then else it never grows. That's interesting. Okay. It's only here that we say that there is a first element. And the rest. When I defined numo, I said something that meant that it's a list with an infinite tail, or with an infinite success of tails, like with where it will infinitely succeed to get more tail to it. Somehow this was the difference. That's so interesting, because earlier I said here, if I constrain it to numo in this way, I actually blow up the search space, and it never ends actually.
This. Okay, I guess you need to be very careful to constrain a list to be infinite. But yeah, I don't fully have the true understanding ingrained yet. Yeah, maybe at some point I would understand how it has to do with the goals being produced in the stream of values that are possible and the branches that are possible. It produces possible branches, so maybe at some point I would understand this exactly, and then this would be like, then this should be obvious what happened when I did this and I said no more here, and then it never ended because it looked for possible values of these. Okay, but yeah, not right now. But yeah, okay, so this works perfectly like this. Yeah, and because this is a little bit hard to read, I can cast it to the symbolic domain or the closure domain. So 5 plus 0 is 5, 0 plus 5 is 5, 1 plus 4 is 5, 4 plus 1 is 5, 3 plus 2 is 5, and 2 plus 3 is 5. Describe the values produced by this. These are all possible values for x and y, where x and y are numbers starting with 0, 1, 2, 3, and so forth, and x plus y is 5. The values are pairs of numbers that sum to 5. Can we define plus o using edero? We can define it, okay. Okay, say plus o. Oh, this looks plus o. This is a bit hard to read for me. I think NMK, where K is the outcome, and then edero, yeah, 0 and K. Yeah, exactly. To generate the pairs of number that sum to 5. Okay. Plus O. Like this. Yes. What is the value of... Give me everything where there's an x and a y, where plus O of x and y is equal to the list that represents the number 5. It's the same thing. Wait, how is this different from what I just said? Yeah, it's this. So 5 plus 0, 0 plus 5, 1 plus 4, and so forth. Now define minus O using plus O. Oh shit. Whoa. wait, I know how to do this. Oh my god. Wait, I'm at this point in this book where I go, whoa, because, holy shit. Okay, wait, this is NMK, maybe they're flipped, but, wait, it's plus O, and then it's like K, and M, or something like that. Let's think through it. So, if I say plus 0 and 5, then the solution of this is 5. So for plus I was saying that n is 0, m is 5, and k is 5. So which two numbers? This number minus this number is this number. So this means k minus m is equal to n. So it means that n is in this position, and k and m, I think they are wait, I just try out. I think there's not many there's not many ways of how to plug this together right now. Okay, so let's say that 5 minus 5 is what? Question mark. A 0. Okay, this would be correct. And then let's say 12 minus 5 or 12 minus 6 is 6, right? Okay, I'm wrong here somehow. So let's flip these. Oh, I'm still wrong. Oh wait, what am I saying? I need to say Byrd number. The 5 5. I get a representation of 0 out. Okay, this was correct. And then here Byrd num and Byrd num. This is 6, I think. Yeah, okay. This is correct. 12 minus 6 was Q. Okay, I just played around until it worked. What is 0 minus 1 or something? Okay, it just comes out to 0. Oh, it comes out to no solution. This is actually great. Yeah, okay. And then 1 minus 1 is 0. Okay, and then 2 minus 1 is 1. Okay, cool. Yeah, and 2 minus 2 is 0 again. Yeah, so I guess 20 minus 2 is a number again. If I say, what is this number? Is 18. Boah, okay. What the hell? This is how minus works. Oh my god. It's flipping the positions of these. This is fucking... Whoa. Whoa. Runs down. Give me everything that is a Q, and then minus O, and then you make a list that represents the number 8, right? Yeah, okay, this is 8, and then another list that is 5, and say that Q is the result of these two. So 8 minus 5, yeah, this is the number that in symbolic domain is called 3 in this way. 3. What is the value of yeah, well, yeah, okay, yeah, I already played around with this. Yeah, what is that? That is an odd number 4 plus 8. Wait. It's an even number. What I'm saying is an even number 4 plus 8 is 12. Okay. 12 minus 12, whatever. Yeah, 12 minus 12 is 0. It's 0. Minus. Yeah, and then now say. Say. A 12 minus 16 is just the empty list. It's basically not figured out. It's just well, it just says there's no solution that goes below the. So no, it's no solution. Sorry, it's no solution. Yeah. Yeah, which makes a lot of sense. It's kind of cute. It's nice. There's no solution. No. 8 cannot be subtracted from 6 since we do not represent negative numbers. Alright, here is length. Yeah, length is kind of like the simplest thing that you could define in terms of a recursion, I feel like. So let me go to a scheme buffer. Define length. L. If L is null, then the outcome is 0, else otherwise it's length in the recursive call and then plus 1. Oh, length. Yeah, and this is for example not tail recursive definition. I don't know if this matters right now. Define length O. Okay. Yeah, what am I doing? Define length O. Okay, it takes a list. Then I write condi. If it's empty, then also it takes an outcome as well. Then the outcome is 0. And otherwise, the list is a list where there is a rest to called D, and then I say, oh wait, I need our numbers now. It's not 0, it's build num 0, which is this representation. Plus 1. One sec. So here it says something like length for L and then the outcome. So I need this outcome. And then I need to say plus so as wait. Also plus the outcome of the recursive add 1 plus 1. So I can write it like this. I can write it like this. Whatever. It's a little bit verbose, but yeah. Pretty sure this is correct like this. Nullo, then so they say an n here. Oops, that was too many. Nesto, also resto. Dres, then say coulda, then plus res this, and then length. Oh yeah, I make a mistake here. This should be the last, and instead of s, they call this res. Okay, for response, I guess, or result. And plus result and then do the recursive call. Yeah, it's funny that basically like you think that, oh, res is not assigned yet or something, but it's not how it works, because it because these sort of run in parallel or something. Basically, de facto, they don't run at all. They just produce the goal. That means all of these 3 goals need to succeed, and the order doesn't matter. I think the order doesn't matter, that's for sure. Except for the leaky abstraction, I guess, that actually you care about the order because of the way that the things get populated with values. It means that you want the recursive course at the end. But I think here it would not matter. No, L. Yeah, there's nothing here that would matter. I think this would not matter if these are so flipped. But sometimes you would constrain the D down to something, and this is important that you do it before the recursive call. Otherwise you would go recursive, and the L would still be anything or something like that. There was a case earlier in the book. There was the difference between an infinite run and something that was able to supply values, I think. No, either way. Okay, so length for run 1. Give me an n, where n is the length of the list. Chikama. Damn, I don't know what this is. Rhubarb. Oh my god, I don't know what this is. And guava. Oh, I feel like that guava is... in German. The guave. Yeah, this is some plant. This is something similar to a lemon or something. Pachyrrhizos erosus. In the Fabaceae, okay. In the P language, P family. Also known as Chikama. I wish I would be able to read this language.
Hikama.
Hikama,
Hikama.
I guess. I guess this means so, or this means rhubarb. It's called rhabarber in German, I know that. Rhubarb. Okay, rhubarb is this... It has this quite special taste. But it's quite popular in Germany for sure. I also like the we usually I also know it from rhubarb pie, and it's quite special because it has a little bit of I'm not sure if this is bitter, but it has quite a special taste. But this is actually kind of like it's called tart taste. And the substance petiose. Okay, yeah, it's the stalk of this plant is edible. It's funny, they have put 3 plants here where for the jicama it's the tuberous root that is edible. For the rhubarb it's the stalk, and for the guava it's the fruit that is edible. Isn't that funny? It's so diverse. Okay, so there are 3 things in this list right now. So what does run length for n say? Oh, it never ends.
Uh, oh wait, what is this? So yeah, this happens to me all the time. Yeah. Okay. So yeah, you get a number out of that. Yeah, that's. You get a logic number out of that. Yeah. That means 3. Okay, so here's something funny. Now I say length of something, and then here I say this is 3. So I get a list with 3 elements. That's the constraint that I put on the list. It goes in all directions. Yeah, here they do this. Actually, they do exactly this. 5 ls list. Yeah. Say run. You can even say star. Yeah. List. And then constrain it down to be 5. Then what you get is a list with 5 elements. 5 element list. What is the value of... Give me everything where there's a queue, and then you say that there's a relationship called length, where the first thing, this is a bit confusing, is a list that also happens to look like a number, but yeah, it's just a list with 3 elements. And here's I say the number 3, the symbol 3, and this just doesn't make any sense. N, this will just not succeed because n is supposed to be a number, so it will fail when it comes to here, and then it will just fail, and that's the end, and it will just fail, and it will be nothing. Okay, run. Give me 3 solutions where there's a queue, and then length of q is q. Oh. Oh. That's funny, yeah. Would this keep going on? No, it wouldn't. Okay. This is only true for the first 3 numbers. These numbers are actually the same as their lengths. This is... Yeah, okay. This is kind of funny. But I don't think this is important. Okay, what is this here? Run for... Yeah, this never ends. Has no value, since it's still looking for the 4th value. We could represent both negative and positive integers as sign bit and then n, where n is our representation of natural numbers. If sign bit is 1, we have the negative integers, and if sign bit is 0, we have the positive integers. We would still use the empty list to represent 0, and of course sign bit could be fresh. Define sumo, which expects 3 integers instead of 3 natural numbers like plus. Oh, that sounds challenging, perhaps over lunch. Go make yourself a Baba Gunash pita wrap. Alter. Okay, wait, I need to Google Baba. Baba. Food? Oder Baba Gunash? Food in Berlin. Baba Ganache. What is Baba Ganache? Easy eggplant hummus. Okay. Baba Ganache. It's Arabic.
Baba Ganoush.
Oh, it's called Baba Ganoush. Okay.
Baba Ganoush. Alright, okay. Also spelled Baba Ganoush or Baba Ganoush. Is a Levantine appetizer. A Levantine knies is the traditional knies of the Levant, in the sense of the rough area of former Ottoman Syria. Okay. Consisting of finely chopped roasted eggplant, olive oil, lemon juice, various seasonings, and tahini. Oh, okay. Yeah, it doesn't sound too complicated. Eggplant is traditionally roasted. Okay, no, it sounds tasty. Baked or broiled on an open flame before peeling, so that the pulp is soft and smoky taste. A maize starter for the regional cuisine, often served as a side. Man, I'm getting hungry. Okay, the book tells me that I should go and make myself a Baba Ganoush pita wrap now, but yeah, like I have a lot of setup to to be able to do this right now. Okay, I'm gonna define sumo. So sumo takes 3 integers. Yeah, n, m, k. Yeah, but now they are basically defined in terms of that there's also the sign. The sign is also allowed. So let me immediately write it in terms of pattern matching. It's easier for me. Okay, so so the first case is the same case that we already had. That is that both numbers are positive. And then in effect, basically drop the sign bits and call plus so. Okay. In the second case, n is. Oh yeah, and the outcome. By the way, the outcome is also positive. In the second case, n is positive, m is negative. Now drop the sign bits. But yeah, drop the sign bits. Remember this, like, yeah. But now I need to handle these in a way where But in order to do this correctly, I feel like that I need to handle, well, there's kind of case 2a, that is that n is bigger than m, kind of. In that case, everything is the same as before. And the outcome is positive. And then there's the second case, where m is bigger than n. There's also the case where they're equal. That is basically here. Then there's the case where m is bigger than n, and in this case, I don't want to just end up with 0. I need to basically say that sort of the portion of m that is bigger than n also needs to be added back or something like that. Like the outcome, first of all, the outcome needs to be negative. And So the outcome is actually, wait. The outcome is negative, and the magnitude of outcome is actually is given by m minus n. Does it make sense? Let's play it through with example data. So if I say that n is 10 and m is 12, and now I say well, m is minus 12 and this is plus 10. Then I say say n plus m, and I go into this case where m is bigger. How do I figure this out? I'm not sure yet. Man, this is actually a real challenge. Damn, I thought I'm gonna write down these 4 cases or something and then I'm done, but now I realize that. So 10 plus minus 12, yeah. Yeah, okay, well, it's true. The outcome, so the outcome sign is negative, and the outcome value is 12 minus 10 is equal to 2. So the outcome is minus 2. This is the thing that needs to happen. But how do I say this one is greater than the other one? It's or is there a trick? Is there some trick? Wait, is there some trick? Is there some other way to get around this? Because here is the first case. So in this case, n is, for example, 5 and m is, for example, 2, and then rv is 5 minus 2 equal to 3. So, well, yeah, it's rv is equal to n minus m, just like we said, basically. Also I should say minus and plus. And r sign is plus. Both are positive, and then there's the third general case where both are negative, and this is basically easy. It just means that rs is negative and rv equal to n plus m values. We call this values here. N plus m is, r value is n value minus m value. The other way around, exactly. And that's the hard part. Differentiate these 2 cases is the hard part. Because the cases where they are both positive and both negative is easy. I just need to
plus the two numbers and then use the sign. And for the cases with the mixed, there's more mixed cases. True. There's also the other mixed case where n is positive, m is negative. Yeah, and then I have again two cases, n bigger or equal m, and m is bigger than n. N is positive, m is negative. So they're kind of the mirror cases, they're the same. Right? I mean, it's for sure there's symmetry in these in this problem, of course, but yeah. If n is negative and m is positive, then the value is m minus n. But yeah, this only works if m is bigger or equal to n. And the sign is negative in that case. And in the other case, I think I will need to flip this, and the value is then this, and the sign is positive, right? It must be, as it's not symmetric in this way. N is negative, like let's say that n is minus 1, and then m is positive, let's say that m is 3 plus 3. In that case, if I say n plus m, what do I only ever need to... Do I only ever need to check which one is negative and which one is positive and things turn out great? No. Yeah, in this case the value will be 3 minus 1, this is 2, and the sign will be positive. Well, yeah, in this case, if this is flipped, then the value will also be 3 minus 1. Yeah, wait, this is interesting. It is the same, it's only that here the... But I do need to say that the bigger number minus the smaller number, this is the difference. So I do need to find the bigger number of the two in order to order this. And then it doesn't matter which one was positive or negative to begin with. So yeah, really the cases 2 and 4 they don't matter. I think if I understand one, I understand the other. This is involved. They say here you should think about it during dinner, during lunch. This is crazy. Okay, will I be able to do this right now? I feel like I need to define a relation that says bigger equal or that takes two numbers.
and it succeeds. It's a goal. It's a returns a goal that succeeds if x is bigger than y. I can write a docstring. A relation where x and y are numbers and x is bigger or equal to y. Okay. So there is a trick. I could go into symbolic domain, calculate it, but yeah, no, then it's not relational anymore. Yeah. So I need to write the relation that means that x is bigger or equal to y. Okay, yeah, let me think about this. Oh, wait. Say x minus y, and that is then bigger than 0. So, or it's okay. I'm gonna say is greater than y. Okay, greater than y. Greater than no. X y. So x minus y and r is at least 1. So poso. And it was, if you say poso to something, the outcome is, yeah, it's a number that is at least 1. Could be 1. Right? Poso Bildner 1 is also true, yeah. But it also succeeds, yeah. Okay. Okay, this is a relation where x and y are numbers and x is greater than y. Okay, so with this, I should, I think, be able to do this. I know I have written down such a large comment. Okay, case 1. They are both positive. This is easy. So here I'm gonna say an R for the rest of R and MR for the rest of M. So these are basically the numbers, and then the outcome will also be a positive number, and that will just be given by plus 1 NR, MR, KR. Okay, this was easy. This was just basically saying, yeah, okay, I'm gonna ignore the sign. Actually, you can ignore the sign. Yeah, if you say, okay, if you say sign here, it's the same sign, so it's gonna be negative. This is the case 1 and the case 3. Both positive and negative are fixed with this case.
Okay, now the case is 4 and 2. Sine A, sine B. Okay, so basically this is equivalent to saying n minus m equal to r, and it splits itself into the r value, yeah, and there you have the problem with what is the value of r. It depends which one is bigger than the other one. Okay, so kr, yeah, has a sign, yeah. Okay, so now there are multiple things true in the world. If mr is bigger than, if nr is bigger than mr, by the way, I can also write the case where nr and mr are equal. In that case, kr is anti-list, and the sign is the sign for 0. So 0 was 0. Oh. They wanted 0 to be represented by the empty list, right? The empty list is 0. In that case, the sign here doesn't make sense. What? Just actually... why? This makes it more complicated right now. What the hell? But this plus this will for sure be not 0, and this minus this will also not for sure not be 0. So this case is still correct. This will just never be 0. Okay. But yeah, in this case, I can't say here sign. I need to say here r as output. Actually, yeah, like this. Is anything? Here I say that. R is nothing. Like this, yeah. N minus m, n minus m. Yeah, if they are equal, if they are the same number, then the result is nothing. 0. Okay, else n is bigger than m. In that case, I can say minus so. And now basically I need to say that there is a sign and a magnitude. I call it v. And then if I call console, this is the sign, and v, the magnitude, the number of k, the outcome number. Then the magnitude of this is n minus m. Okay, like this. And yeah, there's this other case, and in this case it must be like this. There's no other way. Yeah, it must be like this. This is case 2b. The outcome is negative. Oh wait, I forget this. So in this case, where n is positive and m is negative, and then n was bigger than m, then the outcome is positive. So the sign here is 1. This is the sign, was 1, and then yeah, the magnitude is 5 minus 2, yeah, is 3. This is this part. And then in the other case, m is bigger than n, then the outcome is negative. Okay, I'm just gonna trust what I wrote. That this probably made sense. Oh wait, I should, I don't need to say sign here. Yeah, it is. Yeah. And I don't say 1 here. I say Byrd num 1. And here I say, so minus 1. True. Wait. Okay, let me type it out subsymbolically as 1 1. This is the number 1. This is the sign, significant bit, the sign bit, and then 1 for the 1. And here it is the sign. Oh wait, 1 sec. I typed the sign. Okay, now I'm getting tired now. Who's shit? This was only the 1. Yeah, and here was the 0 for the negative. All right. Okay. I'm rolling. I'm here. Okay, m minus n. Okay, I'm pretty sure this makes sense. Yeah. V. Wait 1 sec. V. Here I need to say V. This is the value. Okay, with this I have covered these cases for the 2, and then there are the cases for the 4, and I wonder if basically we can collapse this down. We can collapse this, but let's first write it completely. So in this case, this one was negative and this one was positive. Do I sometimes I wonder, is this a 0? Yeah, this is a 0. Okay. It's the 0 in this ligature. Oh wait, I'm typing an O. What the fuck I'm doing? I accidentally type an O instead of a 0. Okay. It's actually used as, okay, now that I see it, it's very obvious what a 0 is. Okay. So here something is like reversed now or something. So n is negative and m is positive. Then if they are equal, r is just 0. Makes sense, yeah. Something negative plus something positive. If they're equal, then r is just empty. Okay, then there's the case where n is bigger than m. In that case, the value is n minus m. Okay, like here. And the outcome is positive. Oh, this is the same. What? This is, for example, minus 1 plus 3. There you would say that, wait. I need to say m minus n. If I say minus 1 and plus 3, I need to flip this. I need to say 3 minus 1 is 2. This is the magnitude. This value here, yeah. And the sign is positive. So, okay, here. Okay, and here is somehow flipped or something. So if m is bigger than n, then the value is m minus n, yes, and the value is negative. Isn't it always m minus n? It's always m minus n. What? It just flips the sign depending on which is bigger. Does this make sense? If m is bigger than n, then the value is m minus n. If n is bigger than m, then how can the value be? What did I do? What did I... Oh, I have this... wait. Yeah, this needs to be m minus n. M minus n. Why do I think it... Why does this not map? I'll figure it out in a sec. Oh, I flipped the... Oh, no, I flipped the magnitudes. Okay, so n r equal to minus 1. Yeah, well, n is equal to 1, yeah. N is equal to minus 1. M is equal to 3 plus 3. Now the magnitudes is 1. And here the magnitude is 3. Then n bigger than m is not the case. N is smaller than m in this case. So in this case, the magnitude of the outcome is m minus n. M minus n. And the outcome is negative. What? No. The outcome is positive. Alright, okay, so this was this case. For B. Alright. Yeah, I mean, at some point it will be correct. Okay, so, and then here is the other case. Now I have something like... Imagine that n is a large number, like minus 3, so the value of n is 3, and the value of m is 1. So n is bigger than m, and n is a negative number. So the value of this is n minus m. Okay. And the outcome is a negative number. Okay. Now I have like these comments again, so it's hard to read it. I'm gonna make a version without comments. And I had this function, this relation. Alright, okay, so now I have a file where I can actually load the file without compile errors so that I get the full thing. Okay, this looks a little bit like you could simplify something. Isn't this almost... This looks so similar. This just depends on which one is bigger than the other one. So you could say the value is this minus this. So it's also flipped. Okay, no. Okay, so say minus 3. Yeah, this is the minus 3. And minus 3 minus minus 3. Okay, let's see. Wait, no, this is not correct. So they are the same sign, and then they say plus M and K. Oh wait, is this wait, is this 3? No. 6. Ach so, -6. Ah, yeah, -6, yeah. Yeah, -6. Yeah, because this means minus, and then this is -6. True. Yeah, I could. Num signs. So in this case, the first thing is the sign, and the rest is the list. Then you say num list, and then you say 0 minus 1 and 1 sign. Yeah, like this. Like this. Okay, so if I say num signed to here, it's -6. Yeah. Okay, nice. I just defined sumo. Yeah, sumo already works for 2 negative numbers. Now this is positive, then it's 0. Okay, also makes sense. If I swap them, it's 0. Okay, I feel like I should do property-based testing, and I'm making example-based tests. Okay, so this, if I call first and then num signed here, I get 6. It's also correct. And then the hard cases, this is when I say 10, and then plus minus 2. It's the 8, it's the 8, yeah. But if you flip it, oh, it's also 8. So yeah, it's also 8. Yeah, exactly. Yeah. It was, and then that was exactly the hard part. Yeah. And yeah, -2, 10 minus 2. So now I say 20, and this is -10. Yeah, it's correct. And also, if this is flipped, it's -10. Yes. I'm pretty sure I did it correct. Yeah, and I also need it. But yeah. Am I wrong about this? Do I? Correct. But yeah, no, I'm too tired for it. So yeah, this was just an idea. I'm sure that I would figure it out if I'm well rested to simplify this. But yeah, I mean, it's kind of fine, I suppose. Yeah, I'm kind of proud that I figured this out. Alright, this was the bit chapter. This was, yeah, cool, quite intense. Baba Ganache, I think. Okay. Yeah, then see you soon. Code with heart and do great things. Bye bye.